and then in different directions, X and Y. There's a winding number here. And then the similarity matrices can also be separated nicely using the right metric. And if you use the standard metric, people were having trouble to separate it before because they were using standard metric. So we solved the problem by using a different metric. And then the phase transitions have a very sharp, very perfect agreement. And if you do the low dimensional embedding images, well space projection, and again, each dot is a cluster of hundreds of block vectors that belong to each topological phase. This can be done in real space, but you have a different norm distance. It's a different way to measure distance in phase space. So the phase boundaries of this Su-Schrieffiger model real space can also be retrieved. And then, and this is the locally disordered SSH model real space. Again, to choose the right metric, in this case, the L1 metric works better than L2. We did many metrics. This is the one that we found to be the better one. So in conclusions here, and then there is the unsupervised learning is suitable for problems without labeled data and without prior knowledge. Nonlinear embeddings and dimensional reductions are better than linear ones for retrieving topological quantum phase transitions from raw data. And this makes it a bit tricky, because people before they were off, like dimensional reduction is a bit tricky to do if it is nonlinear embedding. If it is linear one, it's easier. The Chebyshev distance for momentum space data and the dual L1 norm distance for real space are better in performance to highlight this topological quantum phase transition, which are more sensitive to these two metrics. And then this manifold learning or linear dimensional reductions, if you equip them with these two distance metrics, can distinguish these phases from non-topological ones, especially when using experimental data and no prior distance information. And this is a very long paper explaining things in every gory detail, and can show you more slides afterwards if you're interested. So thank you for your attention.
Okay, so thank Professor Nori. Very nice talk. So because of a time limitation, maybe we have one very quick, short questions. So.
Hi, thank you for the nice talk. Here.
Volume?
Can you hear me now?
Now it's better.
Yeah.
You need to sing loud.
Okay, thanks. So I was wondering, in one of your examples, you showed that RL is very effective in error correction because it is very effective against single photon losses, right? And I was wondering, since this is also the dominant error in quantum cryptography, so I was wondering if it can be used there as well. But the scenario is really different because we not only want error correction, but also the two parties should be correlated with each other.
Techniques working for problem X are not necessarily working for problem Y and Z, especially for cryptography. It's a completely different kind of game. So I mean, also cryptography is a huge field. So I wouldn't know if this can be applied there or not. This technique should be able to be applied to different kind of topological quantum phase transitions. But the other techniques, we did actually many, it was exhaustive on the tomography one. We just tried essentially everything and tried to see but which ones of these work on cryptography or not, I do not know because it's a completely different field and different kind of questions.
Thank you.
In that case, they're typically looking at Fourier transforms, like periodicities, and you need to factorize, you need to see and so I think the approaches are different. They typically care a lot about quantum Fourier transforms, which we don't care so much about this here. So I think there are different priorities there.
All right, so let's thank Professor Nori again.
Okay, so thanks.